Okay, so let's say that we have an object, a ball or whatever, and let's say that it's launched from a height of 2 meters. At a speed of 20 meters per second. And let's say it's launched at an angle of 40 degrees above the horizontal. And let's say that we want to know how far horizontally the ball travels before it hits the ground. Okay. So the first thing is you have to kind of visualize what's going on, since this is all, there's no figures given with this. So take a second and see if you can just sort of draw a picture of what's going on. Pause the video. Okay, so it's something like this. So here's the ground. And the ball is launched from a height of 2 meters. So this distance is 2 meters. And at the start, the angle that it makes with the horizontal is 40 degrees. So it starts out at that slope and then travels in a parabolic path like that. And we're trying to figure out what this horizontal distance is between where it's launched and where it hits the ground. We're trying to figure that out. Okay, so think first, what's the first step in problems like this? The first thing we have to do is choose our coordinate system location and orientation, and then to choose our time equals 0 and time final. I'm going to tell you a choice just so we're on the same page of the coordinate system location and orientation. I pretty much just always put it on the ground or the lowest point that happens in the problem, and with the y-axis up. So I pretty much always do it like that. And now you have to think about the time equals 0 instant and the time final instant. So pause the video for a second and see if you can think of what you need to do for these two things. Okay, these choices are made based on when, at what instant you have information and at what instant you're trying to find information. We know some stuff about when it's launched. So our time equals 0 is going to be the instant when it's launched. And our time final is going to be the instant when it hits the ground. And I'm going to write it like this. Since I put my origin on the ground, this is going to be the instant that our position is equal to 0. Okay, but this is the instant that it reaches ground level. And now, what's the next step? Now we have to figure out what variables we know and what variables we want. I'm going to list these all out. It's a long list for two-dimensional problems. It was just 6 for one-dimensional problems, but now since we have the x and y components of a lot of things, it goes up to 11. So I'm going to do it in this order. Time final, acceleration, that's an x and y component. Initial position, that's an x and y component. final position, x and y component, initial velocity x and y, and final velocity x and y. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 variables. Okay, well, let's just go through them one by one. So time final, do we know what the stopwatch says when it hits the ground? No, we don't know that. Do we want it? No, if we can get by without it, we're not asked for it, so we'll leave it off. Acceleration, do we know? Yes, it's a projectile motion problem, so the acceleration is always the same. It's 9.81 meters per second squared down. And in this coordinate system, down means negative y component. I'm going to leave the units off, but this is all in SI units. Do we know the initial position, the position at time equals 0? Yeah, we do know that. That is just the coordinates of the object at time equals 0, so that's just this spot right here. So that's 0 for x and 2 for y. Do we know the final position? Well, what we're trying to find is the final x position. So we don't know that, but we do know the final y position. Let's see, I was a little sloppy with this. When I said what our time final is, we can think of like the height is equal to 0. So what does that mean? That means that we know that P final y is equal to 0. But we're trying to find PFX. What about initial velocity? Well, this is where we're going to have to use the angle and the speed. So notice that this initial velocity vector is this, okay? And it has a magnitude of 20 because the speed is 20 meters per second. So you're trying to figure out the components of this vector with magnitude 20 in this red coordinate system. So pause the video and see if you can calculate those components. You should get 15.32 for the x component, and 12.86 for the y component. We got that as 20 times the cosine of 40 degrees, 20 times the sine of 40 degrees. And do we know anything about V final? No, but we're okay without knowing that. We're not asked for it, so we'll leave it off of everything. Okay, so now the question is, can you find an equation that has PFX in it and everything else in the equation is known? Pause the video and see if you can figure out if you can, and if you can, what is the equation? All right, well, if you go through those equations, here's one way to kind of organize it since you'd rather not go through all 6 equations. We know that we're looking for an x component, and so we know right from the start that it can't be a y component equation. So that eliminates 3 of the equations right away. The second thing is we're not trying to solve for TF, and we don't know TF. So all of the TF equations are immediately eliminated. So the only equation we have left would be the equation that says 2ax times the quantity PFX minus blah, blah, blah. And that doesn't work either because we don't know VFX. Okay. So what do we do if there's no equation that gives us what we want. The next step is we try to find TF, see if there's an equation that lets us solve for TF, and then that becomes something known, and then try again. Okay, so see if there's an equation that has TF in it and everything else in it is known. The equation that works for that is PFY is equal to PIY plus VIY times TF plus 1/2 AY times TF squared. So we'll plug all these known values in. So 0 is equal to 2 plus 12.86 TF minus 4.905 TF squared. All right, well, how do we solve this? We have a square, we have a linear, we have a constant. Pause the video and see if you can figure out how to solve that equation for TF. Well, the way we have to go about this one is the quadratic formula. And so with the quadratic formula, this is A, this is B, and this is C. And so we're going to go TF is equal to negative B plus or minus square root of B squared minus 4AC over 2A. And I'll tell you, since this is an online class and you're not doing any in-person tests, just Google quadratic formula solver. You know, you can just do it all online. That's fine with me. So plug your A, B, and C values into a quadratic equation solver, and it'll give you your T's. So do that right now. Pause the video. And the answers that you get, quadratic formula always gives you two answers. And it says negative 0.15 and 2.77. Which one of those do we want and which one are we going to ignore? In this class, we have everything set up so all our times are positive. So we're going to ignore that one. And 2.77 seconds is the time that we're looking for. Okay, now that we know TF, we can go back to this. You know, you can think like, now we have this additional bit of information. TF is 2.77. So now, is there an equation that has PFX in it and everything else in it is known? Pause the video and see if you can come up with an equation that works. Well, the one that should work here is PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. And if you plug in the variables that we know, PFX is equal to 0 plus VIX is 15.32. The last thing that could trip you up here is what's AX? It's easy to make the mistake of putting the negative 9.81 in there, but we're looking for the X component of the acceleration, which is 0. There's nothing making objects accelerate horizontally when they're in projectile motion. So this term goes to 0. Let me change one thing. This TF, I didn't fill that in. We know what that is, 2.77. And then plus 0. So PFX is equal to 15.32 times 2.77. and you get an answer of PFX equal to 42.44 meters. So after you go through this calculation, you know that it's going to hit the ground 44.43 meters away horizontally.